Okay, have you ever really stopped to think about color? I mean, really think about it. Not just your favorite, but what it is. We usually think of it as a chemical, right? Something you mix into paint or a dye that stains a fabric. But it turns out nature has a much cooler and honestly a kind of mind-blowing way of creating color. And no, that's not a trick question. Some of the most brilliant colors you'll find in the natural world, like on this incredible Pollia condensata fruit, have absolutely zero pigment, no dye. It's pure color, made from nothing but its own structure. So, how in the world does that work? Well, believe it or not, the answer is hiding in one of the most common things on the entire planet. That's right. The key to making these amazing pigment-free colors comes from wood. We're talking about a technology that's inspired by nature, using a building block that's been right under our noses the whole time, just, waiting for us to figure it out. It all comes down to cellulose. And cellulose is, well, it's literally everywhere. It's the most abundant organic polymer on Earth. It's what gives plants and trees their structure, from the tallest sequoia to a single blade of grass. It's basically the skeleton of the entire plant kingdom. Okay, so this is where it gets really cool. Scientists take regular old wood pulp and use a process called acid hydrolysis to break it down. And what they get are these incredible microscopic rods called cellulose nanocrystals, or CNCs for short. Now, these things are thousands of times smaller than a grain of sand. You can't see them at all. But these tiny, invisible rods, they're our secret ingredient. So we've got these invisible nanorods. By themselves, they don't look like much. But when you get a whole bunch of them together in the right conditions, they do something truly remarkable, almost like they have a mind of their own. They literally build themselves into a masterpiece. This whole process is called self-assembly, and it's one of nature's most elegant tricks. You don't need some tiny, complicated machine to put everything together. Nope. You just create the right environment, and the basic parts, in our case, the cellulose nanorods, they just spontaneously arrange themselves into this perfect, complex structure. And the process itself is surprisingly simple. You just suspend the nanorods in water, and you wait. As the water slowly evaporates, the rods get packed closer and closer together. Eventually, they're forced to align. But they don't just stack up like a pile of logs. No, they align and then they twist, layer by perfect layer, forming this beautiful spiral-like structure. And here's what it looks like. You end up with this perfectly formed spiral staircase, just on a microscopic scale. Each layer of these nanorods is slightly twisted from the one below it. And this precise, repeating, twisty pattern, well, that's everything, because that is what creates the color. So we've built our tiny spiral staircase out of wood pulp. Big deal, right? How does that actually make a vibrant color? The answer has nothing to do with chemistry. It's all about physics. If you look under an electron microscope, you can actually see this incredible layered arrangement. Scientists have a fancy name for it, a chiral nematic structure. But really, that's just a way of saying it has a twisted, repeating pattern. And the most important part is the exact distance between those repeating layers. That spacing is the key to everything. This whole phenomenon has a name. It's called structural color. So unlike pigments, which work by absorbing certain colors of light, these nanostructures are built to physically mess with light waves. They act like a super specific filter that reflects only one color, one wavelength of light, and lets all the other colors pass right on through. Let's just put it side by side. With a pigment like red paint, it looks red because the molecules in the paint are absorbing the blue and green light. The red light is what's left over to bounce to your eye. But with structural color, it's different. The physical structure is built with the perfect spacing to act like a tiny mirror, but only for red light. It reflects red and lets everything else through. It's the same principle that makes a peacock feather shimmer. And check this out. This experiment shows it perfectly. On the left, you've got a dry film made from these CNCs. Its layers are spaced just right to reflect red light. But then, when you soak that same film in water, the whole thing swells up. The nanorods get farther apart, the spacing increases, and voila, the color it reflects shifts all the way to blue-green. So this is the main takeaway right here. The color is literally programmable. It is physically encoded into the structure of the material. If you can control the spacing between those layers of nanorods, you can control the exact color it reflects. It's this fundamental direct link between a tiny structure and the color we see with our own eyes. Now, this is all amazing science, but let's be real. A film that changes color every time it gets wet isn't exactly practical for, painting your car.
So scientists had a big engineering problem to solve. How do you turn this beautiful, shimmery film into a tough, practical pigment you can actually use?
The first big problem they had to tackle was something called iridescence. Because the color comes from this flat, ordered structure, the color you see actually changes depending on the angle you're looking from. Just think about a soap bubble or the back of a CD. It's pretty, for sure, but if you want a stable paint color, you need it to look the same no matter how you look at it. So the goal was crystal clear. In the words of the researchers themselves, they needed a pigment with, and I'm quoting here, a consistent visual appearance across a wide range of viewing angles. Basically, a solid, stable color that doesn't shimmer and change. And the solution they came up with was just brilliant. Instead of letting all the nanorods assemble into one big flat film, they thought, what if we could get them to self-assemble inside millions of tiny, separate droplets instead? So here's how they pulled it off. They took the water with the nanorods in it and mixed it into oil, which created all these microscopic droplets. Inside each tiny droplet, that same self-assembly magic happened. But, and here's the clever part, as the droplet dried and shrank, its surface didn't stay smooth. It buckled and folded in on itself, creating this complex, crumpled shape. And that crumpled surface scatters the reflected light in all directions, which completely solves the iridescence problem. By solving that iridescence problem, researchers have really blown the doors open for a whole new class of materials. I mean, this isn't just a new way to make a color. It's a totally new way to think about what materials can do. And the potential uses are just huge. I mean, because this pigment is just made of cellulose, it's totally non-toxic and biodegradable. Imagine vibrant paints, makeup, or even food coloring, all made from wood. And because the color is linked to its structure, you can make smart materials, like a coating that changes color to let you know when the humidity is too high. Now, of course, it's not totally perfect just yet. The final pigment is super sustainable, but the process to actually get those cellulose nanocrystals out of the wood pulp in the first place uses some pretty strong acids and a lot of water. So a huge area of research right now is figuring out greener, more efficient ways to do that, to make the entire process sustainable from start to finish. And that kind of leaves us with a really fascinating thought. We've just seen how we can literally program color into the physical structure of a material as common as wood. But if we can teach a material to be a specific color, what else can we program it to do? What's the next thing we're going to teach wood to do?